This is a walkthrough of a Further Maths A-Level Further Pure 2 paper. Question number 1, Part A. Show that the transformation W is equal to Z minus 1 over Z, where Z is not equal to 0, maps to the locus the modulus of Z minus 1 equals 1 in the Z plane onto the locus the modulus of W is equal to the modulus of W minus 1 in the W plane. Okay, first thing we're going to do is to take our transformation and rearrange it to make Z the subject. So we have W is equal to Z minus 1 over Z. We times both sides by W, so we get WZ is equal to Z minus 1. We move the Z terms to the same side, so we get this, and then the next step after that I'm going to factorize out the Z. So I get Z, and in brackets W minus 1 is equal to minus 1. After that I'll divide both sides by the brackets. I'll get Z is equal to negative 1 over W minus 1. So now I'm going to substitute this into this locus here. So replace Z with negative 1 over W minus 1. So that means that Z minus 1, or the modulus of Z minus 1 equal to 1, is now going to become the modulus of negative 1 over W minus 1 minus 1 is equal to 1. Right, we want to put all of this together here. So we'll write negative 1 as minus W minus 1 over W minus 1. When this is all put together, so you've got negative 1 minus negative 1, which is 0. So you're just left with negative W at the top over W minus 1. And the modulus of that is equal to 1. The rules of moduli say that you can change this to the modulus of the top over the modulus of the bottom. Now the top bit here, the modulus of negative W is just a negative of the modulus of W. Then I'm going to times both sides by W minus 1. So I'll get the modulus of W is equal to the modulus of W minus 1. Let's have a look. Is that what we want? Yep. So we can just say as required. The region Z minus 1, or the modulus of Z minus 1, less than or equal to 1 in the Z plane is mapped to the region T in the W plane. Part B, shade the region T on the Argand diagram. Now we've just shown in part A that the transformation W will transform this locus into this locus. So the modulus of Z minus 1 equals 1 gets transformed to the modulus of W is equal to the modulus of W minus 1. Now they ask us about this region. So we've got the modulus of Z minus 1 less than or equal to 1. So you'll notice it's pretty much identical apart from the less than or equal to sign. Now we need to think about what's going to happen to that less than or equal to sign that we would have had, or we would put here. Where's that going to end up in our final result? Now it's going to end up here the same way round. So this symbol, so if we put it here, it's going to end up here. Let's just show that. So if I have that there, it'll be like that, because at no point in these steps did I multiply or divide by a negative number to meaning I'd have to flip that sign around, so there's no need. So this region is going to transform to this region, the modulus of W less than or equal to the modulus of W minus 1. Okay, so let's draw the axis for our Argand diagram. So we've got real and imaginary. Now when you get this type of region or loci, then it's going to be the perpendicular bisector between 2 points, and those 2 points are going to be 0 and plus 1. So I'll just mark 0, I'll mark plus one here, and I want the perpendicular bisector between those 2 points. Now it needs to be a solid line because I've got the equal to symbol. So let me just put a solid line here, and I'm just going to mark down that that is at a value of 1/2. And with this type of loci, remember the symbol points to the side that you need to shade. So I need to shade the side that's towards the left hand side, towards like the W side. So that's going to be this side over here. So let's do that now and just shade off this side like that. Question 2. We have this matrix A here, 3 by 3, which is 1, 0, 4, 0, 5, 4, 4, 4, 3. Part A. Verify that the vector 2, negative 2, 1 is an eigenvector of A and find a corresponding eigenvalue. So we start by multiplying the vector 1, 0, 4, 0, 5, 4, 4, 4, 3 by this vector, and that's 2, minus 2, 1. Now if it's an eigenvector of A, I should get a multiple of this vector, and the multiple that it is the corresponding eigenvalue. So let's multiply this out. So we'll start with the top row, and there's only one column in our question, so there's only going to be one column in our answer. So 1 times by 2 plus 0 times by minus 2 plus 4 times by 1 gives you 6. So you basically got 2 plus 4, 6. The next element, 0 times by 2 plus 5 times by negative 2, that's negative 10, plus 4 times by 1, so negative 10, plus 4 is minus 6. And then the last one, bottom element, 4 times by 2, which is 8, plus 4 times by negative 2, that's minus 8, so we've got 0, plus 3 times by 1, which is 3. And I can see that the original vector gets multiplied by 3 to give me this vector. So it is an eigenvalue vector, and its eigenvalue is 3. So we'll write down, so since, so you should write some sort of conclusion, 6 minus 6, 3 is equal to 3 lots of 2 minus 2, 1. 2 minus 2, 1 is an eigenvector with eigenvalue equal to 3. Part B, show that 9 is another eigenvalue of A and find a corresponding eigenvector. Right, so if 9 is an eigenvector of A, then this characteristic equation will be equal to 0 with lambda equal to 9. So let's write out what that characteristic equation would be. So you know that you would have 1 minus lambda here. So if I make lambda 9, so that will be 1 minus 9, so that will give me negative 8, 0 and 4, then I have 0, and then here I would have 5 minus lambda, so if I made lambda 9, 5 minus 9 is minus 4, and then in the bottom row I would have 3 minus lambda, so I'm making lambda equal to 9, so 3 minus 9 gives me minus 6. So I want to find a determinant of this and see if it equals to 0. Right, so let's start with the negative 8. That's going to get times by negative 4 times by negative 6, which is 24, minus 4 times by 4, which is 16. Then I'm going to have minus 0 times by, now I could actually leave this out because it doesn't matter what I put in the brackets, it's just going to be 0, but I'll just put it in for completion anyway. So it'll be 0 and then times by 0 times by -6, which is 0, and then minus 4 times by 4, so minus 16, and then plus 4 up here, and that's going to be times by 0 times by 4, which is 0, minus 16, so that's plus 16. Right, now what does this equal? -8 times by 8, and then plus 4 times by 16. Well, that is just minus 64 plus 64, which is equal to 0. So since this characteristic equation, the determinant of a minus 9i is equal to 0, 9 is an eigenvalue of a. Now we need to find the eigenvector. So we take a 104, 054, 443. The vector we're trying to find, we'll just call it x, y, z. And we know we're going to end up with 9 lots of x, y, z. So let's form those equations and solve them. Right, so we will have x plus 4z, x plus 4z is equal to 9x. Right, so that basically means that 4z is equal to 8x. I can divide everything by 2, and z is equal to 2x. Second row, 0x, 5y plus 4z. 5y plus 4z is going to equal to 9y. So if I take away 5y from both sides, I've got 4z is equal to 4y. So z is equal to y. And then the bottom row, 4x plus 4y plus 3z is equal to 9z. So that gives 4x plus 4y is equal to 6z. I can divide everything by 2 and get 2x plus 2y is equal to 3z. Okay, so if I made x equal to 1, that means z is equal to 2, because it's 2 times x, and y is going to be equal to z, so it's also going to be 2. And I'll just make sure that works for the last equation. So I should get 2x's 2 times 1 plus 2 times 2, so this becomes 6 on this side, should equal 3 times 2, 6, yep, so it works. So I found the eigenvector corresponding to the eigenvalue 9, and in fact you could have any multiple of this vector as an answer. Now, given that a third eigenvector of A is the vector 2, 1, minus 1, part C, write down a matrix P and a diagonal matrix D such that P inverse AP is equal to D. Now remember, P is the matrix of eigenvectors and D is the matrix of eigenvalues. So I have the eigenvalues of the first 2 eigenvectors, but I don't have the eigenvalue for this eigenvector. So that's going to be my first step, is to find the eigenvalue for this vector here. So we'll take our matrix 1, 0, 4, 0, 5, 4, 4, 4, 3. We'll multiply it by the vector 2, 1, minus 2, and we're going to see what multiple we end up with. Right, so 1 times by 2, which is 2, and then 0, and then minus 8. So 2 minus 8 is minus 6. Next one, 0, 5 minus 8. So 5 minus 8 is minus 3. And then the bottom row, we have 8 plus 4, which is 12. And then 12 minus 6, which is 6. So if I look at the multiple, I can see that it gets multiplied by -3. So with this eigenvector of 2, 1, -2, it has an eigenvalue of -3. Right, let's start now by writing the vector P, or sorry, the matrix P. So this will be my eigenvectors. So I'm going to do the 3, the 9, and then the -3, do it in that order. So I will have 2, -2, 1, 1, 2, 2, and then 2, 1, -2, and then my matrix D, this diagonal matrix, needs to have the corresponding eigenvalues in the correct order. So 3, 9, -3. So 3, and then 9 along the leading diagonals, and then -3. And that completes, oops, let's highlight the answer, and that completes this question. Question 3, part 1. Lottery X requires each player to buy a ticket and choose 5 different numbers from the numbers 1 to 45 inclusive. Lottery Y requires each player to buy a ticket and choose 6 different numbers from the numbers 1 to 35 inclusive. A player wins if their chosen numbers match completely those drawn at random by the lotteries. A person wishes to play one of these 2 lotteries. The price of a ticket to play each lottery is the same. The prize money for winning each lottery is the same. Decide which lottery you would recommend that they play, giving a reason for your answer. Right, so let's start with lottery X. And if we have a look at lottery X, we're choosing 5 numbers from 45 numbers. So the number of possibilities is going to be 45C5. If we do that on our calculator, we get 1,221,759 different possibilities. And for lottery Y, so for lottery Y, we're going to choose 6 numbers from a set of 35. So the number of possibilities is 35C6, and that gives 1,623,160. Now we will have a greater chance of winning when there are fewer outcomes, and lottery X is the lottery that has fewer outcomes, 1.22 million roughly compared to 1.62 million roughly. So I've finished with the conclusion that I would recommend lottery X as there are fewer outcomes than lottery Y, and I've put a comparison of the 2 outcomes at the end there. Use Fermat's little theorem to show that when 128 to the power of 129 is divided by 17, the remainder is 9. So here's a reminder of Fermat's little theorem. It comes in 2 forms. We need to decide which form we're going to use. Now remember, P is the prime, and that's 17. And that means that A is equal to 128. Now, does P divide A? So does 17 divide 128? No, it doesn't. So 17 does not divide 128. So by Fermat's little theorem, we know that we're going to be using this second form here because P does not divide A. So we can now start writing out our congruence equation, which is going to be 128 to the power P minus 1, so that's 17 minus 1, is equal, or sorry, congruent to 1 under modulo P, so that's going to be modulo 17. So we've got 128 to the power 16 is congruent to 1 modulo 17. Now what I want to do is to get up to the power 129. Now I think I can get up to the power 128 because 16 times 8 is 128, yeah? So I'm going to raise both sides to the power 8. So I'll have 128 to the power 16 raised to the power 8, and then on the other side 1 to the power 8. So both sides are raised to the same power. So now what I'll have is 128 to the power 128, because we just multiply the power. 16 times 8, 128 is congruent to 1 to the power 8 modulo 17. Now we want to get up to the power 129, so what I'm going to do now is to multiply both sides by 128. So I've got 128 to the power 128. I want to times that by 128, which is basically like 128 to the power 1. So if I do that to the other side as well, like this, and then what we'll have is 128 to the power 129, which is what we want, is congruent to 1 to the power 8 times by 128 and modulo 17. Now we can simplify the right hand side so that we have basically just 128. That's what this is going to work out to be. So now we're going to work out the least residue or the remainder when we do 128 under modulo 17. Now 128 is actually equal to 17 times 7, so 17 goes into 128 7 times, with a remainder or a residue of 9, because 7 times 17 is 119, then 119 plus 9 gives you 128. So we can finish this off. So we've got 128 to the power 129 will give us, or is congruent to 9, which is our remainder, modulo 17. So we can finish off, always finish with a conclusion. Therefore, the remainder when 128 to the power 129 is divided by 17 is 9. Part 3 of question 3. There are 3x chairs in a room. When these chairs are set out in rows of 7, there are 2 chairs left over. Part A, form and solve a congruence equation for x. Okay, so let's have a look at the information that we've been given. We have there are 3x chairs in a room. They're set out in rows of 7, and then there are 2 left over. So the number of chairs in the room, 3x, is congruent to a remainder of 2 left over when we do modulo 7. Now let's work out how many solutions this congruence equation has, and we'll do that by working out the greatest common divisor of 3 and 7. Well, since we're dividing by, or we've got a modulo of a prime number, then that means we're just going to have one solution. The greatest common divisor of 3 and 7 is 1. Okay, we want to be able to divide both sides by 3. We can't do that yet. However, if I add 7 to the 2 and get an equivalent and write down 9, So 9 is going to be modulo 7 is equivalent to 2 modulo 7. Now, because I've got it written as 3x is congruent to that, I can now divide both sides by 3 and then get x is congruent to 3 mod 7. So that makes the one solution that we're expecting. Okay. Given that there are at least 100 chairs and that 1/3 of the chairs can be arranged exactly into 5 equal rows, part B, find the least possible number of chairs in the room. So what we're going to do is take our answer from part A and use that to find other possible values for x, and we can just keep adding 7 because these are going to give the same residue or remainder under modulo at 7. So I'll just keep adding 7s, 17, 24, 31. And what I want is to keep going until I find a number that is divisible by 5, and that will satisfy this part here about the chairs being arranged into 5 equal rows. So we'll keep going, keep adding 7, so we're on 38, 45. Okay, there we go. So we'll have x is equal to 45. So this represents the 1/3 of the chairs that can be ranged exactly into 5 equal rows. We need to find the least possible number of total chairs in the room. So that will be 3x, which will be 3 times 45. And that will give 135 chairs, and that also satisfies this condition about there being at least 100 chairs in the room. Question 4, part 1. Two distinct elements of a group G are A and B. The element A has order 5 and A cubed B is equal to BA cubed. Prove that AB is equal to BA. Okay, now if we've got this element A which has order 5, that means A to the power 5 is equal to E, the identity element. Okay, and we're going to be using this in our working. If we get an A to the power 5, we can replace it with the identity. So let's start with the information we've been given, which is A cubed B is equal to BA cubed. Next, I'm going to multiply both sides by A cubed on the left. So we've got A cubed and then A cubed B is equal to A cubed BA cubed. Now, since we were given in the equation this A cubed B is equal to BA cubed, it means that if you multiply by A cubed on the left, it's the same as multiplying by A cubed on the right, which means on the right hand side I can move that A cubed across so it's on the right. So I'll have BA cubed times by A cubed. We'll multiply that out and we'll have A to the power 6B is equal to BA to the power 6. Now you'll probably see at this point why I chose to multiply by A cubed, because I wanted this A to the power 6, because this is like A to the power 5 times by A to the power 5 is the identity, so that just leaves A, B, and then the same on the other side, B, A to the power 6, A to the power 5 times by A, so that's the identity times by A, which just leaves A. So we prove that statement as required. Given that P, Q, R and S are distinct elements, part 2, part A, check each of the group axioms for the set A is equal to P, Q, R, S under the operation circle with a little cross inside defined in the table below. So we've got this table here. So the 4 group axioms are closure, an identity, inverses and associativity. So let's start with closure. Now all of the elements in the table are members of the set A, so the set is closed under this operation. So we can tick off the first one it satisfies the first axiom. So the second one we need to look for is identity. Now we just need to state or find what the identity element is, and we're looking for the row and column where the headings remained unchanged, and that is going to be the element P. You see it doesn't change the headings, so we can just state that the identity element is P. So we'll tick that off, and the next we're looking for are inverses. Now, since P appears in every row and every column, that means that every element has an inverse, and in fact, each of the elements is self-inverse. So that can be ticked off. So we're now down to the associativity axiom. Now, if the group is associative, then both of these calculations here should give me the same answer. So we're going to go through each one and see if we do get the same answer. So the operation of Q and R under this operation will give me Q, and if I do Q and S from the table, I get R. Right, we want to see if this gives us the same thing. So we've got the operation of Q and whatever RS is from the table. So from the table, that is Q. And if I do QR from the table, just having a look, that's Q. So it fails the associativity check. So we'll put here not associative. Right, so moving on to part B, hence determine whether the set A forms a group under that operation. Well, it doesn't meet all four axioms. It fails with the associativity axiom, so it doesn't form a group. So I'll just write down that since the operation circle, cross, whatever you want to call it, is not associative with these elements anyway, that means the set A is not a group. Question 5. We have I sub n is equal to the integral between 0 and pi over 2 x to the power n cos x dx, where n is greater than or equal to 0. Part A, prove that for n greater than or equal to 2, I sub n is equal to pi over 2 to the power n minus n times by n minus 1 times by I sub n minus 2. Okay, now to do this question, we need to do integration by parts. So I'll just write out what we've been given here, and we'll do u is equal to x to the n, which means du dx is going to be n x to the power n minus 1, and then we'll do dv dx is equal to cos x, which means that v is equal to sine x. Right, so let's do that and see what we get. So uv, so that'd be xn x to the power n sine x between the limit 0 and pi over 2 minus the integral of v du dx. Now there's an n here, constant, so let's put that on the other side, the integration sign, leaving x to the power n minus 1 sine x dx. Now we're going to do integration by parts again on this part here. So I will just change these bits. So this time doing integration by parts on this bit here, x is going to be, or u is going to be x to the power n minus 1. So du dx is going to be n minus 1 times by x to the power n minus 2. dv dx is sine x, let's keep the colours the same, which means that v is equal to negative cos x. Right, so let's carry on with that. So we've got the part from before, x to the power n sine x, with limits of 0 and pi over 2, then minus n times by, so it's uv again, so x to the power n minus 1 times by negative cos x uv, then minus the integral of v du dx. Now you've got a minus here and a n minus 1, so we're going to take the minus across, so that now becomes a plus, and we're going to take the n minus 1 across as well, so n minus 1, and then write the rest of the integral, so that's 0 pi over 2, and actually this bit here also needs to be between the limits of 0 and pi over 2, and that leaves x to the n minus 2 times by cos x dx. We stop because this matches up with the original integral, so we'll be able to swap that out in a moment. Let's tidy up the rest of this and then put the limits in. So let's start here. We'll have pi over 2, so we're putting that limit in first, to the power n, and then times by sine pi over 2, and then minus, I'll put it all in actually, even though it's going to become nothing, 0 to the power n sine 0. Okay, so that's all of that first bit here done. So minus n, and then what we'll have is 0 to the power n minus 1 times by negative cos 0, and then we want to subtract from that, sorry, that should be pi over 2, shouldn't it? We're putting pi over 2 in first, so let's do that. So pi over 2, and then cos pi over 2, like that. And now we'll put the 0 in, so minus 0 to the power n minus 1 times by minus cos to the, or cos 0. So that's that first bit done, and then plus n minus 1, and then all of this part here can be changed to I sub n minus 2, because this bit is the same as what we started with, but instead of n we've got n minus 2. Okay, so there are any things that are 0, well sine 0 is 0, so we can forget about all of that. Cos pi over 2 is 0, so we can forget about all of this, and all of this as well, because 0 to the power anything, that's going to be 0. So what are we left with? So pi over 2 to the power n, because sine pi over 2 is 1, minus, and then it's going to be n times by n minus 1 times by I sub n minus 2. So compare that to what we had. So that's equal to in as required. Figure 1 over here shows the vertical cross-section of a proposed flood defence system. The cross-section of the flood defence system is modelled by the curve with equation y is equal to 1.2 x to the power 6 cos x plus 0.2, where x is greater than or equal to 0 and less than or equal to pi over 2, where x and y are measured in meters. The area R shown shaded in figure 1 is bounded by the curve, the y-axis, that's here, the x-axis, that's here, and a line with equation pi is equal to x over 2. The flood defence system will come in hollow sections that will be filled with water once they are in place. Each section will have a length of 10 meters. Part B, use the model and the answer to part A to estimate the volume of water needed to fill each section. Well, the first we want is that result or answer from part A, which I've written down here. So I'm going to start by finding the area of this cross section, which is going to be the integral of this 1.2 x to the power 6 cos x dx. Then we've got this plus 0.2, so I guess I could put the plus 0.2 here, but really I want to match this up to what I had in part A, so I'm going to separate that and put plus at 0.2 dx and then put my limits in 0 pi over 2, 0 pi over 2. Now what I'll do is work out this part separately and put that to one side and add that onto my answer at the end. So when I integrate that, I'm going to get 0.2x, and then between these limits of 0 and pi over 2. So basically it's just going to be 0.2 times by pi over 2. So that gives pi over 10. So I'm going to highlight that because that needs to get added on to my area at the end while we deal with this part here. Yeah, so let's deal with this. So using what we had from part A, this is basically 1.2 lots of I sub 6. And using the formula we have here, that's going to be equal to 1.2, I'll put some brackets here, and I6 is going to be pi over 2 to the power 6 minus 6 times by 5, which is 30, I sub n minus 2, so I sub 4. Now we're going to work out what I sub 4 is. So that'll be my next step. So I sub 4, again, we're just using the formula again. So this will be pi over 2 to the power 4 minus 4 times by 3, which is 12, I sub 2. And then we'll move on to work out I sub 2. So I sub 2 will be pi over 2 squared, so we're still using this, and then minus, and then we're going to get 2 times by 1, which is just 2, so minus 2 I sub 0. And then we've just got this last one to work out what I sub 0 is, so we'll do that here. So I sub 0, so we're going to put zeros in for n, so we will get 0 to pi over 2, so we've got x to the power 0, and anything to the power 0 is 1, and then cos x, so all we're left with is the integral of cos x. So we're going to evaluate this, so we'll integrate cos x, that's going to be sine x, between these limits of 0 and pi over 2. So sine pi over 2 is 1, sine 0 is 0, so that's going to be 1. Right, so let's put this all together now. So we're going back to this, so let me just draw an arrow. We're taking this and putting all these different parts together and see what we get. So we've got 1.2 times by pi over 2 to the power 6 minus 30, I'm going to leave plenty of brackets here, I4, and what's I4? That's pi over 2 to the power 4 minus 12 I2. Okay, so what's I2? It's this. It's pi over 2 squared minus 2 I0. And what's I0? 1. That's easy enough. Right, so let's close the brackets. So you've got those to close, these to close, and then a third set to close. Let's see what all of that gives us. Okay, so this gives us 1.08707 and so on. So this is the area of the cross section. What we need to do is to estimate the volume. So we'll need to times this by 10 to get the volume. So that's giving us 10.87027 and so on. Let's give that to three significant figures. So we'll go for 10.9 meters cubed, and that will be correct to three significant figures. Each section can be filled with water at a maximum rate of 175 litres per minute and is required to be filled with water within 1 hour of being put in place. Part C, use the model to decide whether this requirement can be met, showing all your reasoning. Well, the first thing is that 1 metre cubed is equal to 1,000 litres. So the volume that we have of 10.870271, if we times that by 1,000, we get a capacity of 10,870.271 and so on litres. Now if we take that and we divide it by the number of litres per minute, so we'll divide this by 175, what we get is 62.1158 minutes. Okay, well, this 62.1158 minutes is greater than 60 minutes, so it's greater than an hour. So what's our conclusion? The requirement will not be met. It's just slightly too long. Question 6. Figure 2, which is down here, shows the curve with parametric equations x is equal to a cos cube theta, y is equal to a sine cube theta, where theta is less than 2 pi and greater than or equal to 0, and where a is greater than 0. Part A, find the total length of this curve in terms of a. So this is the formula we use when we want to find arc length for a parametric equation. Here I've got theta, not t, so I just need to think about that. So I have x is equal to a, and I'm going to write it as cos theta cubed, just makes it easier to differentiate. So I'll have dx d theta is equal to 3a cos squared theta sine theta, using the chain rule. And actually when you multiply by the inside differentiate, it's going to be minus sign, so I need to put a minus here like that. So dx d theta, I'm now going to find dy d theta, so y is equal to a sine theta, I'll write it like this, cubed. So then dy d theta is going to be equal to 3a sine squared theta times by the inside differentiate, just cos theta, so there's no minus there. So my arc length is going to be the square root of my dx d theta all squared, so that's minus 3a cos squared sine theta squared plus dy d theta squared, so that's 3a plus, sorry, not plus, times sine squared theta cos theta d theta. Now what can we do with this? So we can square both of the brackets. So we'll have the square root of 9a squared cos to the power 4 sine squared theta plus 9a squared sine to the power 4 theta cos squared theta, with the d theta at the end. Now I'm going to take out the 9a squared as a factor, so 9a squared, and I can also take out a sine squared plus cos squared as a theta, sorry, not as a theta, as a factor of both of the terms. So if I take that out, actually thinking about it, it may be better to explain it this way, that I'm taking out a sine squared cos squared as a factor. That makes a bit more sense. It's easier to understand because every term's got sine squared cos squared, and then what that will leave me with is cos squared theta plus sine squared theta, so it all multiplies out. Right, so what's going to happen here? Well, this is just 1, okay, so that's going away, so bye bye. Then 9a squared, if we square root it, because remember what we can do is we can square root this and we can square root this. That's just 1 there, so the 9a squared becomes 3a. That's a constant, so let's lob it to the other side of the integration sign, and we've now just got the square root of this, which is just going to be sine theta cos theta d theta. Now to integrate this, what we've got here is half of the double angle formula for sine. I'll just put a reminder of that. So 2 sine theta cos theta is equal to sine 2 theta. So if we divide both sides by 2, this is going to be half of sine 2 theta. So this is equal to 3 over 2. There's my half sine 2 theta d theta. Now I can integrate this because the inside is linear, and just use the reverse chain rule. And now we're going to be thinking about the limits. So we've got 3 over 2a, and then if we differentiate, sorry, if we integrate this, we integrate the outside, that becomes minus cos, so minus cos, and then we need to, remember the inside doesn't change, we need to divide by the inside differentiated, so we need to divide by 2. So if I move my divide by 2 over here, I now get divide by 4. Let's now think about these limits. Okay, so let's consider this part of the curve and see if we can work out what the limits are going to be. Okay, so let's start here. So at this point here, y is equal to 0. So that means that this is equal to 0. And this part is going to equal to 0 when theta is equal to 0. So we've got theta equals 0 here as one of the limits. If we look at this part here, this is where x is equal to 0. That means that this part is equal to 0. And this is going to be 0 when theta is pi over 2. So pi over 2, that's going to be my theta. So that gives me the limits now, 0 and pi over 2. And I know that once I've worked this out, I need to times this answer by 4, because this is only going to give me this section here. Right, time to put the limits in. So we have minus 3/4a, and that's going to be times by the cosine of 2 times pi over 2. So that's going to be cos pi. And then minus negative 3/4a times by the cosine of the lower limit, 0. And that's going to get times by 4. Okay. So cos of pi is negative 1. If you times that by negative 3/4a, we get 3/4a. And then we've got minus minus. Now cos of 0 is 1. So we get negative 3/4a times by negative, so plus another 3/4a. And then we're going to times that by 4 because we're only working out one of these arcs. And it's all symmetrical, so we times it by 4. So 3/4a plus 3/4a. that's 3 over 2a, so we've got 3 over 2a times by 4, which gives me exactly 6a as the total length of that curve, or arc length. The curve is used to model the design for a new suite. The curve is rotated through pi radians about the x-axis to create the shape of a suite. The suite is to be covered in chocolate. Given that the total length of the curve is 5 centimeters, part B, estimate the surface area of the suite that is to be covered in chocolate. Now, before we get onto the maths, just a word about this suite. Look at the pointed edges. I would not want a suite like that in my mouth. It would get torn to ribbons. So anyway, let's go on to the maths. Now, a couple of things. First of all, this is the formula for the surface area of revolution when it's a parametric equation, which is what we've got in this question. And this part here, the square root of the derivatives squared, we worked out in part A. That was this square root, which actually simplifies to 3a sine theta cos theta. So we'll be able to just slap that straight in there when we work out this question. Okay, so let's do that. So we've got 2 pi times by y, and y is this a sine cubed. So a sine cubed theta, and that's going to be times by 3a sine theta cos theta d theta. Now we've got these a's, we can actually work out a because it says given that the total length of the curve is a, and we worked it out in part A as 6a. So using that we can work out what a is. So 6a is equal to this 5 centimeters, which means that a is equal to 5 over 6. So we can start to tie this up a bit. So 2 pi, and then we've got 3 times by 5 over 6 times by 5 over 6 again, 3a squared. So that becomes 25 over 12. And then we'll have sine to the power 4 theta cos theta d theta. Right, let's move the 25 over 12 across, so we'll times it by 2, and that gives us 25 over 6 pi, and then this integral of sine to the power 4 theta cos theta d theta. So this one fits an integration pattern, and that integration pattern is this one where you've got the derivative times by the function to the power n, and that's going to be equal to that function to the power n plus 1 over n plus 1 plus c. So what we will get now is 25 over 6 pi, and then the integral, it will be sine to the power 5 over 5, so it's going to be 1/5 sine to the power 5. Now we need to work out what our limits are going to be. Now the actual formula for the surface area of revolution will actually rotate whatever curve you have 360 degrees, so all the way around. So that would actually create half of the suite. So using the limits of 0 and pi over 2, what we need to do is, once we've worked this out, we only need to times it by 2, because the formula is going to rotate this a full 360 degrees. Yeah, just that quarter, and that will give you half the suite. So this just needs to be multiplied by 2 to give us the full surface area of the suite. So we can tidy this up, so we can do the 25 over 6 pi times by 5 times by 2, and that gives 5 pi over 3, and then we'll put our limits in. So we'll put in the limit of pi over 2, so that'll be a sine of pi over 2, and that's going to be to the power 5 minus sine 0, again to the power 5. That doesn't make a difference because it can be 0 anyway. Let's see what that gives us. So this part's going to work out to be 1 minus 0, so it's just 1, so we're just left with 5 pi over 3. Okay, so that's going to be an exact answer, or if we wanted to, we could give a decimal answer. So it's 5.23598. So we'd go for 3 significant figures. That'd be 5.24, and I presume this is in centimeters squared. Okay, so let's just highlight that. And we'll move on to the last question. Question 7, part 1. Solve the recurrence relation un plus 2 is equal to un plus 1 minus 9un plus 4, where n is greater than or equal to 1, and where u1 is equal to 4 and u2 is equal to 7. Okay, so the first thing I'm going to do is just rearrange this and write it as un plus 2 minus 6un plus 1 plus 9un is equal to 4. So I'm going to start by forming and solving the characteristic equations. That's going to be m squared minus 6m plus 9 equals to 0. So that gives me m minus 3 all squared is equal to 0. So that gives me a repeated root of m is equal to 3. And when I have a repeated root, that will give my complementary function as a plus bn, where a and b are arbitrary constants, times by the root 3 to the power n. Now, because of the form of what I've got on this side, for my particular integral, I'm going to try lambda because I've just got a constant. So if I then substitute that into here, I'll get lambda minus 6 lambda plus 9 lambda is equal to 4. So actually, what do we get? Lambda minus 6 lambda minus 5 plus 4. So we've got 4 lambda is equal to 4. So that means that lambda is equal to 1. So that's my particular integral. So now my general solution is going to be my complementary function plus my particular integral. So that gives me a plus bn times by 3 to the power n plus 1, and that is equal to un. Now we want to find our particular solution by finding the value of the arbitrary constants. So we'll start with n is equal to 1, and we'll substitute that in here. So we'll have a plus b, and that's all times by 3 to the power 1, so times by 3 is equal to, and I'm going to move the 1 across, so u1, that's 4, and then 4 minus 1 is 3. So that gives me 3a plus 3b is equal to 3. So let's just highlight that for a minute. And now I'm going to make n equal to 2. And when I've got n equal to 2 in here, I'll have a plus 2b. And that's going to get times by 3 squared, so it's going to get times by 9. Again, I'm going to move the 1 across, and then on this side I put u2, which is 7, take away the 1, which is 6. So the second equation I get is going to be 9a plus 18b is equal to 6. So we want to solve these two equations simultaneously. Now, if I take the first equation, 9a plus 18b is equal to 6, and then take the second equation and times it by 3, I'll get 9a plus 9b is equal to 9. Then I'll subtract, So I'll have 9b is equal to minus 3. So if I divide both sides by 9, I'll get b is equal to negative 3 over 9, which is going to be negative a third. Now if I substitute that into this equation here, let's do that. So I'll have 3a and then 3 times by negative a third, which is going to be minus 1, is equal to 3. So we'll have 3a is equal to 4, and then a is equal to 4 over 3. So let me just highlight those two values. B is negative a third, a is 4 over 3. So now I can write my particular solution, which is going to be un is equal to, so I want to go back to this here, a, which I've got as 4 over 3, plus, well, it's actually minus a third, so it's going to be minus a third n, so minus 1/3 n, times by 3 to the power n plus 1. Now I could leave my answer like that, or what I could do is take one of these 3's out from here, so then that becomes 3 to the power n minus 1, and use that 3 to multiply these, and then I'll get 4 minus n. So either one of those would be our solution for the recurrence relation, our closed form. Part 2, question 7. A sequence x1, x2, x3 is defined by n plus 1 times by x n plus 2 plus x n plus 1 minus n plus 2 times by xn is equal to 0, where n is greater than or equal to 1, x1 is equal to 2, x2 is equal to 5. Prove by induction for n in the set of positive integers that xn is equal to 1/8 of 25 plus 3 times by 1 plus 2n times by negative 1 to the power n. So first of all, I start one basis step, and I want to prove that this statement is true for x1 and x2. So this is what I'm going to get for x1, and that becomes 1/8 of 25 minus 9. 25 minus 9 is 16. 1/8 of 16 is 2. So I can see it's true for x1. Now we're going to see if this statement is true for x2. So this is what the statement becomes. And this becomes 1/8 of 25 plus 15. In other words, 1/8 of 40, which is 5. So statement is true for x1 and x2. Next step, we move on to our assumption. So we're going to assume the statement is true for xk and xk plus 1. So we start with xk, so this is where we make n equal to k. So we take this statement here, and everywhere you see an n, we put a k in. So I'm just going to highlight that so you can see, and we're going to do the same for xk plus 1. So same thing again, write this statement out, replace all the n's with k plus 1. And here we are, xk plus 1, n is now equal to k plus 1. And you can see that k plus 1 substituted where we had k before. Now comes our induction step, and that's where we're going to take xk and xk plus 1 and put it into this recurrence relation so that we can get an expression for xk plus 2. So for xk plus 2 in this recurrence relation here, we actually need to make n equal to k. So this is the recurrence relation that we have, and I'm just going to rearrange this to make this k plus 1 times by xk plus 2 the subject. So that's done here. So now I'm going to replace this xk and this xk plus 1 with the statements that I had in my assumption step. So here we go with the substitutions made. Now it may be useful at this point just to write down what it is I need to get to so I can see what it is that I need to factorize out. So I've written that down here, and basically it's this statement with wherever I have n replaced with k plus 2. So that's going to be here, and then the 2n, 2k plus 2, and a negative 1 to the power k plus 2. So if I know this is what I need to get to, that should make the process that I'm going to do now a bit more fruitful rather than just randomly doing things. My next step is just to expand these brackets here, so times everything here by k, and then everything here by 2. And then in the second set of brackets, I've just expanded this, so I've got 2k plus 2 plus 1, so I've got 2k plus 3. My next step is going to be factoring out this 1/8 and then see how much of these terms here I can simplify. So I will have 50 here minus 25, so I will just have 25. Then we have the 25k here. Now I'm going to work my way across these other terms. Now I've just expanded the brackets here, so 3k plus 6k squared. But because I want this negative 1 to the power k plus 2, I'm going to write negative 1 to the power k plus 2. But to keep it balanced, I need to do negative 1 to the power negative 2. And that will become the same as negative 1 to the power k. So I'm going to continue on. The 50 we've already dealt with. We put that and taken away the 25. I'm going to expand the brackets here. So I'll have 6 plus 12k. And I'm going to do the same thing with the power and do k plus 2. And to balance it out, negative 1 to the power negative 2. Then the 25, that's been dealt with. And then I expand the brackets here, so I get 6k plus 9. And I'll do the same thing, the power. I want this to the power k plus 2. So to balance it out, do negative 1 to the power negative 1. And that will become the same as this, power k plus 1. So let's see what we can do about simplifying this. Well, these two terms I can put together and write as 25 and in brackets k plus 1. I want to be able to do the same with the other term because I need to be able to sort of cancel this k plus 1 out. Right, so now we've got the last term since we've expanded these brackets. Let's see what we can do. So I've got all of these terms to the power k plus 2, which I'm going to put together. So this negative 1 to the power negative 2, well, that's just going to be 1. But here, this negative 1 to the power negative 1 becomes a negative, and we're subtracting these negative terms, so we add them on. So if we put all of these terms together here, this is what they come. I just realised I forgot the negative 1 to the power k plus 2, so I've put that back in here. And then what we have is that this factorizes, and actually what it factorizes to is 3 times by k plus 1 times by 2k plus 5, and then we've got negative 1 to the power k plus 2. Now, because we've got the k plus 1 on the other side, and now we've got it here, they're all going to cancel out. And this 2k plus 5 is the same as 2k plus 2. So you expand that, you get 2k plus 4. Plus the 1 makes the 2k plus 5. So we're now on our last step, which is that xk plus 2, so we've got the formula that's required, is 1/8. So quite a lot of algebra here. 25 plus 3, and then in the brackets, the 1 plus 2k plus 2, that makes the 2k plus 5, which is what we wanted. And then we times that by negative 1 to the power k plus 2. So you can see we've got the k plus 2's here, here, and here. And I'll just finish it off by closing that bracket off. And then we'll finish off with our conclusion. So if true for n equals k and n equals k plus 1 and shown to be true for n equals k plus 2 and true for n equals 1 and n equals 2, then true for all positive integers by mathematical induction.